Very good. Shall we go on?
Yeah, great. This break allowed me to go over everything about the standard and to take in the knowledge that we saw of the different materials. I think I'm ready for us to look at the geometric analysis of the cutting tools.
Very good. The geometric analysis completes what we have already seen on the part about materials. Do you know what? I have something that may be useful for you.
What's that?
Look, I love this drawing because it shows you the configurations of the tool and how they adjust to the shape of the piece to be machined.
Perfectly clear. I think to make the head of the pawn, for example, I would use a tool from the M family.
Fine. And we also have, for example, the Z tool or G tool that we could use for cutting and separating our piece from the rest of the material.
Perfect.
In short, geometry of this tool is defined by the geometry of the piece that we are going to machine. And this is the analysis that we're going to make now.
And is this also standardized by the ISO standards?
Yes. And do you know what? I have something that can help you out. Look. The ISO standard has defined a particular coding for the classification of the geometry of the tools, which uses 10 different codes, which will define the type of insert, the angles, and other things, which is what we're going to see now. First, we have the shape of the insert. There are inserts with different geometries that are circular, square, triangular, or diamond-shaped. The shape of the insert is conditioned by the geometry of the piece that I want to make. Let's see. Let's take the case of our pawn. For example, two tools with different geometries. We can see that depending on the shape that we want to achieve in the insert that we have, we can achieve a more or less precise version of the piece. In this case, the square insert, as you will see, cannot perform this operation.
Of course. Essentially, I must define which geometry of the insert allows me to achieve the design of the piece.
Very well. Secondly, we have the angle of the incidence. If we take a cutting tool like we can see here, the angle of incidence is defined by a vertical tangent to the cutting surface in the front face of the insert. Now what happens if I have different loading angles and I subject them to the same weight? As you will see, the first insert, whose loading angle is smaller, suffers a small deformation, while the insert with the bigger loading angle suffers a much larger deformation.
So it's better to have inserts with small angles of incidence?
That would be correct for roughing operations, where we remove a lot of material and therefore we need a more robust insert. But if we want to perform finishing, we should use a bigger angle of incidence since the machining forces will be less.
Okay, so a large angle of incidence for finishing, a small angle of incidence for roughing.
Thirdly, what we have are the tolerances. I define tolerances as the variation between the nominal value and the actual value of our insert. Now if I have my piece to produce the following insert, I can achieve the following result. If the insert needs to be replaced, it may be the case that the piece to machine is out of tolerance due to the variations in the geometry of the insert.
Uh-huh. And how can I prevent this?
Well, we have two options. Either we can adjust the values of the new dimensions of the insert, which means a cost since we have to stop the production process, or we can buy inserts with smaller tolerances, which in turn are more expensive. Let's see, by the way of reference. When I want to perform roughing operations, the dimensional tolerance of the inserts is not decisive. But, however, in the case of the finishing, I need to ensure I achieve the dimensions and tolerances of the piece specified in the plan. Therefore, the tolerances of the insert take on greater importance. The next point, number 4, is the type of inserts. When it comes to selecting the type of insert, we must take into account certain considerations. the type of holding system, the cooling method, and the shape of the chip breaker. The type of insert holding system, the support plate, and the chip breaker as required may be this shape or this other shape. The cooling method determines the type of insert to use. In this case, the coolant enters under a chamber where it is then driven by pressure to the cutting edge. In another possible configuration, the coolant enters through the rear part and circulates through the chip breaker channels to the cutting edge. Finally, we have the shape of the chip breaker. Its shape determines the output radius of the chip. The smaller the radius, the easier to the break chip, but a smaller radius implies greater forces.
And why is a shorter chip more useful?
Well, the thing is, if the chip is long, it can get tangled up and collide with our cutting tools, which causes damage to the insert.
Okay, it's logical that we want to have a shorter chip. This expands the useful life of the tool.
Exactly. We have point 5, which is the CI. The CI value complements the concept of tolerances. CI is a characteristic size of the insert that varies according to geometry. Look at these examples. The bigger the CI value, the bigger the size of the insert. Therefore, it is normal to have greater tolerances, so we will use higher CI values for the roughing tools and lower CI values for finishing tools. Let me show you how the table works. Based on the geometry and the CI dimensions, we can determine the CI term of the ISO nomenclature. Then we have point 6, which is the thickness. The thickness of the insert is another characteristic size of the tool associated with the robustness it has.
So less thickness means less robustness.
That's right. We have point 7, which is the tip radius. Each insert has a tip radius. Now then, let's take two different inserts and carry out a machining operation at the same speed. We can see that at the same speed, the circular insert achieves a better finish than the diamond-shaped insert. In order to achieve a better finish, I have to slow down the forward motion speed.
Yes, but this increases the cycle time. Isn't it a good idea then to use an insert with a large tip radius? I have a better finish in less time.
That's right, provided that the geometry of the piece doesn't condition you. In the case of our pawn, we can see that we can't use a circular insert since we can't copy its shape. Therefore, we must make a balance between the finish that we want and the forward motion speed and the geometry of the piece to be produced. We have point 8, which would be the geometry of the cutting edge. When using inserts with this type of geometries, we achieve a better finish, since the crack which is formed on the piece is controlled. The problem is that the force that is exposed to may deform the insert.
But how do I solve this?
Well, there are two options. Either we remove smaller amounts of material, which implies longer cycle times and increased insert wear, or change the angle of the attack on the insert. In this way, I get more robustness, but form bigger cracks.
But if I change the angle, I lose finishing.
Exactly. The key lies in the type of operation to be done. If we want to carry out roughing, we can use the second option since finishing is not a problem.
Of course, and for cutting, it could pass to the first tool since I have much less material to remove.
Perfect. The last two terms of the nomenclature refer to the information on the chip breaker and type of coating of the insert. You can see that the coatings are classified by the families of materials that we saw before. Therefore, we have coatings P, K, M, N, etc. Very good, Joaquin. We have now seen the different terms that describe an insert. Likewise, the standard specifies how to describe the tool holder. Something that I'd like to show you are the holding system shapes. As you can see, depending on the holding system shape, different geometries can be achieved.
Well, Jorge, I see the selection of the cutting geometry is also a science. Essentially, we saw that the standard simplifies the work, defining 10 types of terms to describe the inserts.
Very good, Joaquin. Perfect.
And each of these defines the properties of the insert. It's a question of doing the analysis beforehand and then writing the associated code, right?
Good, Joaquin.